Hey, what's going on guys? Tanmay here for Simple Snippets and welcome back to another video tutorial on data structures and algorithms, and let's continue with our graph data structure topic. So if you've missed previous couple of videos in this DSA course, or if you're new on this channel, in the previous two videos of this playlist, that is data structures and algorithms, we've started off with the graph data structure topic and we understood what is a graph data structure. We theoretically saw examples, we saw the structure, we compared it with tree data structure, and also understood the different terminologies and definitions that are involved with a graph data structure. So if you are absolutely new to graph topic, please check out those two videos. But now let's move on with the application side, the practical side, which means that now that we've understood what is a graph data structure theoretically, how exactly would it be implemented when it comes to computer science, when it comes to actual coding, right? Because we want to write algorithms, we want to do some coding using this graph data structure. We want to apply the different standard operations in graph data structure, and in order to do that we need to understand how it would be implemented using a code, that is implemented using different structures, right? So one of the methodology to implement graph data structure is by using adjacency matrix, and that is the topic for today's video. We're going to understand what is the adjacency matrix and how it enables us to implement the graph data structure. So let's quickly take a little bit of theory and then we will see with example and diagram what is the adjacency matrix. Okay. Now if you want to note down this definition, you can take a screenshot or note it down. But talking about adjacency matrix is a way of representing a graph. So this is what I already told you, because we want to implement graph data structure, right? So we have to implement it using some methodology. One of the methodology is adjacency matrix, and it is used to represent a graph as a matrix of boolean values, zeros and ones, which I will show you in a minute. And a finite graph, which means that it would have some finite number of vertices, can be represented in the form of square matrix on a computer, where the boolean values of the matrix indicate if there is a direct path between two vertices. Now of course this sounds a little difficult when you just read it, when you just read the theory, but let's take a look at it in a diagram kind of way. So let's assume there is a matrix of n cross n. Now when you're talking about matrix, when you come across this word matrix in computer science, generally it means a 2D array. So a 2D array also represents a matrix. Mathematically you can call it a matrix, but when it comes to computers, when you're using certain data structures, we use a 2D array. So let's name that ADJ or A or adjacent n cross n. So this is a n cross n 2D matrix. That is a 2D array. I hope you know what is 2D array. I have tutorials on 2D array separately in C++ and Java playlist. You can check that out. But if you know basic arrays, I'm pretty sure you know the concept of 2D arrays, right? So the concept is that if there is an edge, that is if there is a path from one vertex I to j, then we have to mark aij as 1, that is adj of ij equals to 1, and if there is no edge from vertex I to j, then we have to mark it as 0. So diagrammatically, let me just show you an example. So taking our example of the current graph and this being the matrix, so this is how a 2D matrix would look like, or a 2D array would look like, right? We have rows and we also have columns, right? So the number of rows and number of columns would be equal to the number of vertices. Right now the number of vertices in this graph are 1, 2, 3, 4, 5 and 6, right? So n, let me write n somewhere, n equals to 6. So that's why we have a 2D matrix of 6 cross 6 starting from 0, because remember array indexes start from 0. So this is a 2D matrix, correct? Now here you can see I have given a representation of the name. So each vertex name corresponds to a particular index value in the 2D matrix. So A is considered as 0, B is considered as 1, C is considered as 2, and so on and so forth. We'll talk about this later on. But according to this criteria, if there is an edge from I to j, so is there an edge between A to C? Yes, we can see there is an edge. Now this is an undirected graph. We'll talk about directed as well as weighted, unweighted also in a minute. But let's just currently mark all the ones and zeros in this 2D matrix, in this 2D array, using these two criterias, and then we'll talk further. So if there is a path between A to C, yes, there is a path. So from A, let's start with row. So for A, it is the first row, that is the 0th row. And for C, we have to consider the column. So is there a path between A to C? Yes. So the cross section where A and C meet, that is this cell, we have to mark as 1. Okay? Makes sense? So I'll mark this as 1 because ADJ of A and C is gonna be equal to ADJ of, what is the row number of A? 0, right? I've already mentioned it over here. It would be 0. And what is for C? It is 2, right? C is 2. And this we have to mark as 1 if there is a path. So this will be marked as 1. So you can see in the 2D array, we are putting number 1. Similarly, we have to fill out this entire 2D array or 2D matrix with ones and zeros depending upon whether there is an edge between the two particular vertices or not. So I'll quickly fill them up and then we can talk about it as we move ahead. Okay, so I've filled the entire matrix, entire 2D array with 1 wherever there is a connection. So if you see, is there a connection between A to B? Yes. Similarly, since this is an undirected graph, there is also a connection between B to A, right? In undirected graph, you can traverse both ways. So if you see B as the row and A as the column, this is where one more connection is. That's why it's 1. So in undirected graph, whenever there is a connection between one vertex with the other vertex is also connected back to it, right? So the matrix is always going to be symmetric in nature. So when I say symmetry, it would mean that if I draw a diagonal across this matrix, it is going to be a mirror copy. So this and this is going to be a mirror copy of itself. But this is only applicable when it is an undirected graph, which means that there is both way traversal. If it is a directed graph, it is not necessary that if you can traverse from B to D, it is not necessary that you can traverse back from D to B. It depends upon the arrows, right? So in that case, this 2D matrix will not be symmetric in nature. So I hope you get the idea. Now remaining boxes or the remaining areas where there is no connection, you have to add a 0. Okay? Now this is how a adjacency matrix is, and this is how you can represent a graph with 2D array. Now this was unweighted graph. So when you talk about weights, you apply some numeric values to the edges, right? So let's say this graph is a weighted graph and it represents the interstate or intercity travel, right? So let's say traveling from city A to city B is 10 kilometers. From city A to city C, it is 20, right? So in that scenario, instead of ones or instead of where there is an edge between two vertices, instead of writing 1, we take the weight values. So from A to B, that is from A to B, instead of writing 1, we will write 10. Okay? That's the only change. So I just wanted to let you know how the naming or how the numbering goes. Okay? So that is for weighted graph. Coming back to our unweighted or non-weighted or undirected graph back, let's talk further. So now that you've understood how you can use a 2D array in computer programming to represent a graph data structure practically, we also now need to think about the efficiency of representing a graph data structure using adjacency matrix. Now what do I mean by that? When I talk about efficiency, it means the time and space complexity that involves when you perform operations on graph data structure when implemented as adjacency matrix. Let me repeat that again. So when I'm talking about efficiency, it means that I'm talking about the time and space complexity involved when you implement graph data structure as this adjacency matrix or as this 2D array practically. Now again, we've already talked about space and time complexity in 2 separate videos in this DSA course. I've tried to simplify it as much as possible. Please watch those videos if you have any confusion. They're important because as you move ahead in your programming career, as you start implementing difficult algorithms, time and space complexity plays an important role. It might not be as important right now as a student, but as you progress, time and complexity plays a very vital role. So the reason why we're talking about time and space complexity of implementing a graph data structure using adjacency matrix is because there are other ways also to represent graph data structure. So of course we need to compare which one is the best, right? And how do you compare two different methodologies to implement the same data structure? You compare their performance, and the performance is the time and space complexity. So let's talk about that. So for a graph data structure, some standard operations could be to find a particular node in a graph. So let's take our current example, and let's say we have 6 nodes or 6 vertices A, B, C, D, E, F, right? So n is the number of vertices equals to 6. And let's say I want to find whether we have the vertex E in this entire graph or in this matrix. So how do you figure that out? Now looking at this graph, you can say that each indice of the 2D matrix, whether it is row or column, represents one particular name of the vertex, right? So you can easily traverse one particular row or one particular column to figure out whether this particular node exists or not. Now when I say E, it means that I want to find out the value inside the node E, right? So in the graph you can see E is the name of this node or vertex, but the value inside it is 87. So basically we are searching for 87. So this E can be an object which will have a data member, let's say value, which is 87. So we want to find out 87. So for that, you can create a separate list or a hash table. And I know we've not talked about hash tables so far in this DSA playlist, but we will talk about it in future. But basically hash table is another data structure where you pass a key and you get a unique value. So h of key will give you a value. So when you pass h of A is the name of the vertex, you will get this particular indice only. Similarly, since I want to find out E, when I pass h of E, I will get this exact particular value, which is 4. So this means if you store all the names of the vertices in this hash table, you can immediately find the particular value in O of 1, which is constant time. Or if you're storing it in a conventional list, of course you'll have to go one by one. You'll have to figure out which one you're searching for, and then in that scenario it would be O of n, because n is the number of vertices that you have. So larger the number of vertices, larger the time, but a hash table would be much more efficient, right? Because you pass a particular name and you get the value. Now in case if you don't get anything, let's say I'm searching for a random thing that is not there in the graph. Let's say I'm looking for vertex z. Now we don't have z, right? So h of z will give us null, but it will be immediate and there will be only one particular operation. So it would be constant time. Correct? Moving on, let's talk about finding all adjacent nodes for a particular node. So this is again one more standard operation. So let's say I want to find out all the neighbors of the vertex B. So what do? First thing, you'll have to figure out the index for vertex B. How do you do that? You will first search this list or hash table, right? Let's say we're using hash table for this instance. So when I say h of B, I will get the unique index 1. So this takes constant time. So O of 1 plus, now I also want to figure out all the neighbors. I hope you know what are neighbors. Neighbors are the immediate vertices which are connected to it. So for B, we have one neighbor A, we have one neighbor C, we have one neighbor F, we have E and D. So basically we have 1, 2, 3, 4, 5 neighbors. I'm sorry, F is not directly connected. We have 4 neighbors, right? So now that we've got the index of 1, we can simply go to this 2D matrix, find the row which corresponds to B, which is given by this index. So B is represented by this index in this row, and traverse this entire row and figure out where the value is 1. Wherever there is 1, it would mean obviously that there is a connection. So traversing this one particular row will take how many iterations? It would take iterations equal to the number of vertices, which is 6, which is basically O of n, right? So it will vary depending upon the number of vertices. So larger the number of vertices, the larger the number of entire row that we have to traverse and figure out where there is 1 and where there is 0. And then you get the count. So overall you can see O of 1 is used or is required to find out the index of this particular vertex which is assigned in the hash table. So this is constant time plus the entire iteration of this particular row to figure out where there is 1 for every connection, and that is nothing but linear time. So basically O of n is the time complexity to find all adjacent nodes of a particular node where n is equal to the number of vertices. Lastly, again, to check if there are two nodes connected, what do you need? You simply need the name of the two nodes, correct? So how do you figure that out? Well, let's say you want to find out whether there is a connection between B and E. So you'll pass B and E, right? So the first step is to figure out the indexes of B and E, right? So B is 1 and E is 4. So basically you want to find out whether there is a connection of 1 and 4. These are the index values. So that's step 1. So step 1 is, again, you'll get these values in constant time, because when you pass B in the hash function h of B, you'll get unique value as 1. You'll say h of E, you'll get the unique value as 4. So you've got the indexes that you have to check in this 2D matrix. So that happens in constant time. So I'll say O of 1. Plus, now you simply have to go to this particular cell in this 2D matrix. So you'll have to say ADJ of 1, 4, is it equal to 1? So let's go to 1, which is this cell for B, and 4 is for E, and which is that cell? This is that cell, correct? Is it a 1? Yes, which means that there is a connection. So again, this is also happening in constant time. You simply get the coordinates, or you can say index values, and directly jump to it. You don't have to traverse this entire row or entire column. You simply fetch these two indexes from the hash table for the particular vertices and directly jump to it and make that check. So again, this is also happening in constant time. So O of 1 plus O of 1, which means that it takes constant time to figure out whether there is a connection between two vertices or not. Now all this is possible when you actually first store the names of the vertices which are mapped to their particular indexes using a hash table, okay? Otherwise it would take O of n to figure out the particular index for that particular vertex, because you'll have to traverse this entire list and find out the corresponding index for that particular vertex, and then you'll have to come back to this matrix, okay? So this is the basic time complexity in general. There are other operations also, but some standard operations I just wanted to show you. The efficiency of adjacency matrix, which is pretty high, but there is a catch over here, that is the space complexity is not linear. It is actually quadratic, which means that the number of cells in the memory that are required to create an adjacency matrix is directly proportional to n square. N is the number of vertices. So if you see, if you have 6 vertices, you will have 36 cells. That is 6 square, right? So if you count these cells, you will get the total of 36. Now 36 might sound very less, but imagine a graph which has, let's say, 100 vertices. So if you have 100 vertices, the space that it will occupy in the memory, practically when you implement graph as adjacency matrix, would be equal to 100 square. Now that's a lot of memory, right? And this is again only for 100 vertices. In real world scenarios, we have many nodes, right? How many number of cities can you imagine? Maybe there are 1000 number of cities, and 1000 square is a lot again, correct? Let's imagine a social media site like Facebook. It has like 1 billion users. So 1 billion square can be a lot of memory, right? It is a huge memory. So this is one drawback of adjacency matrix, that is space complexity. And generally adjacency matrix is used when the graph is dense. What do I mean by that? That means that there are a lot of connections between vertices. That is, a lot of vertices are connected to many others, which means that majority of the vertices are connected to itself. That would make all the zeros as 1, or maximum number of zeros as 1. In that case, the adjacency matrix makes sense, because if you observe right now, this adjacency matrix, only the numbers where the number is 1 is actually important, right? The other values or the other cells where there is 0, there is no connection. But when you practically implement this 2D array, this will still occupy some space in the memory, which is actually of no use, which means that we are wasting a lot of memory. So in case if there are very less connections, let's say there was no connection between A to C or A to B, or even more less connections, then the number of ones would have reduced over here, which means that the number of zeros would have increased and we would have wasted even more memory. So right now also you can see all these number of zeros are basically nothing but wastage of memory. So you don't want to do that. So that happens when the graph is sparse, which means that there are fewer connections. Okay. And also adjacency matrix is generally preferred when the number of vertices is small. That is, the count of vertices is small, because as I mentioned, the space complexity goes on increasing to the power 2 as the number of vertices increase. So if you have limited space, you cannot practically implement adjacency matrix methodology to implement the graph. Okay. Alright, so this was a brief about adjacency matrix being used to implement graph data structure practically. And as I mentioned, there are other methodologies also, like adjacency list, which is another famous way of implementing graph data structure, which we will see in further video. But I hope the concept of adjacency matrix is now clear, and how you can use adjacency matrix to implement graph data structure practically, because now you can create a program, create a 2D matrix and implement the graph data structure, which of course we will see in future. We are gonna write some code, we are gonna implement graph data structure, but before implementing we need to understand how and the different ways in which graph data structure can be implemented, hence the theory on adjacency matrix. Okay. Alright, so I'm gonna wrap up this video over here. I hope you've understood the whole adjacency matrix methodology of implementing graph data structure. In further video we will take on adjacency list as well and understand the pros and cons of that particular methodology or that particular implementation style. If you like this video, please give it a thumbs up. Let me know in the comments how this video was. Do share it with your friends, and I'll see you guys in the next video. Peace.